Hello everyone, in this tutorial I'm going to show you how to simulate a 2D adhesive joint. We're going to concentrate on stress analysis, not failure, in this tutorial. So we have two adherents made out of aluminium, each with 100 millimeter length and 3 millimeter thickness. And then we have adhesive in the bonding area, which is 25 millimeter. Because all the units are in millimeter, I'm going to use the SI millimeter unit system. So this is going to be millimeter, Newton, ton, second. Stress is going to be megapascal. Energy is going to be millijoule, and density ton over millimeter cube. Okay, so now let's start with a part. I'm gonna first create a part. Now I'm going to give a name to this one, call it adherent. So I want this one to be 2D, deformable and shell, and approximate size 200 is okay because I'm going to use a millimeter unit system. Click on continue, and I'm going to just draw a rectangle from here to here, and give a dimension to this one. From here to here is 100, and from here to here is 3 millimeter. Okay, so click on cancel here and click on done. So this is my adherent, and so what I'm going to do, I'm going to rename this one, and I'm going to call this one adherent top, and then I'm going to have one for the bottom. So I'm just going to copy this one, and I'm going to change the name here to bottom and click on OK. So as you can see, I have both adherent at the top and adherent at the bottom. So now the next step is to create a adhesive. So right click here, create, and call this one adhesive. Again, 2D planar deformable shell. Click on continue, and I'm going to create again another rectangle and give a dimension to this one. Let's make it 25, and the thickness is 1 millimeter. So cancel the procedure and click on done. So we are done with this. What I want to do in the next step is to create a material property. So if I go to property here, click on the create material, I can write at the top aluminium. So we're gonna again use a very simple material property. So it's gonna be elasticity elastic, and for Young modulus I'm gonna add 70 megapascal. So the Young modulus for aluminium is 70 gigapascal, and if I want to write it in a megapascal form, I should write it 70,000 megapascal. And Poisson ratio is 0.3, and click on OK. And I'm going to do the same for aluminium, for adhesive. So I'm going to type adhesive, and this is going to be a brittle adhesive, so elasticity elastic. And for Young modulus, I will use 7,000 megapascal again, and Poisson ratio 0.29, and click on OK. Next step is to create a section. So currently we are in adhesive. I'm going to go to adherent, and I'm going to create a section for aluminium. I'm going to call this one RL. So we're going to have solid homogeneous. Click on continue, and here I'm going to select the aluminium. So this is the important part. So because this is in 2D and we don't have any let's say width in a Z direction, so as you can see now everything that we have in a Y and X direction, so there is nothing in the Z direction, but in reality we don't have anything in 2D. Everything has a width in a Z direction. So here's the place that we're gonna add that thickness. So if I activate this one, plane stress strain thickness, then I can make this one 25, which is like a width of the sample that is going to be in Z direction. Click on OK, and now I'm going to assign this to a section. So this one, aluminium, and then I'm going to go for a top. I'm going to apply this one to aluminium. Click on OK, and next step is go to do an adhesive one. So create adhesive. Oh, so I've already created adhesive. Yeah, so I'm going to create a section for adhesive. So it's going to be adhesive, and again solid homogeneous. Click on continue, and this time I'm going to select adhesive, plane strain, stress strain thickness. Again same thing, 25. You have to make sure that the thickness are same. Click on OK and assign this one to here. Click on OK and select the section, this time adhesive, and click on OK. So now we have our material properties for adherent top and bottom and adhesive. Next step is assembly. So first I'm going to import the adherent top and the adhesive by holding Control, and I'm going to activate the auto offset. So it's not really going to change anything because the adhesive anyway is at the top there. So click on OK. So what I want to do, this is a adherent top. So what I want to do, I want the adhesive to go in this area, and obviously we have to define a contact between the adhesive and adherent. We can actually define a contact without partitioning the adherent by defining, for instance, a tie contact that I want to do interaction. So I can use the tie contact to tie basically this line to the top line of the adhesive, and later I can apply a assembly. So we have two options here. I can use a tie contact, which is basically I'm saying to software that the contact between the adherent and adhesive is perfect, so there is no failure. In real life, it's not like this. We only use this for a stress analysis. So if you want to do a failure analysis, then we have to use some sort of like a contact surface to surface contact or cohesive model, and which is like we have a two different type of cohesive model, which can be a surface cohesive or element cohesive. If you want to know more about this, I have a course that is related to specifically about adhesive and composite material, and you can get that one and know more about failures in adhesive. But the aim of this tutorial is only for beginners, so we only I'm going to only show you the very basic stuff about Abaqus. So as I said, I have to define a contact between this line and this line, but it's not really good if I define a contact for the whole line. This will increase the computational time. So what I have to do, I have to create a section cut or partition that is 25 millimeter, so I can only define a contact for a very small area of this line. In order to do that, because I selected my instance type as a dependent, so I have to do all my change in a part. So I'm going to go on a part, and if I go to the top one, I want the partition to be in this area. So I'm going to use yes, this one, partition face sketch. So I'm going to click on this, and I'm going to draw a line from here to here, and I'm going to say from here to here is 25 millimeter, and cancel it, click on done. So as you can see, I have this partition, and if I go to assembly, you see that if I want to apply a tie constraint, I can only apply for this small line rather than the big line, which increases the computational time. So before adding any constraint, moving this adhesive to a correct location, I will define interaction between these two lines. You can do that after assembly, but I normally prefer to do that before assembly, because if you do assembly, then you have to remove and add a selected part to be able to select the line, but here is much easier. So I'm going to go to create constraint, select the tie. So it says choose the master type. This is I think this is Abaqus 2019, so it uses a master and slave, and I think that they got rid of this. Now they call it primary and secondary in the newer version. So for the master type, select the surface and select this one, click on OK, and for other one select surface again, so that's going to be a top one, click on OK, and keep the parameter as it is and click on OK, and then go back to assembly and go to create constraint and select this point and this one. Okay, so if you want to know more about interaction and the definition of each of these, please check the videos that I have in this course about the interaction. So if the first of this course start with explaining of all of these modules individually. So if you want to know more about the interaction, the difference between a tie and surface contact, please check that video. before doing this video. So now I'm going to do the bottom one. So again, assembly at the adherent bottom. Make sure that you activate this one. So now this time I want to create another partition, but this time on the left side. So I'm going to go to part again, select the adherent bottom, and select the same thing here, partition face sketch, and again draw one line and give a thickness, give a dimension to 25, and cancel this. So I have a partition. If I go back to assembly, you'll see that I have a partition in the correct location. And then I'm going to go to interaction again, create another tie constraint, and it says to choose the master. Make sure that you always choose a master on the stronger part. So because in this case the adherent is aluminium and is stronger in terms of properties, it's always better that you choose the stronger as a master. And also you have to choose the one as a master that is not going to fail. So for instance, imagine if you define a failure criteria, you normally define a failure criteria in adhesive, because you're going to have a failure normally in adhesive rather than adherent. So you don't want the master to be in a part that it's going to fail, because that will cause a problem later. So I'm going to choose a master, again top surface here, and slave this one, click on OK, and click on done. And then I'm going to go back to assembly, create constraint, select this one, and then select this one. So as you can see, we have our single lap joint, which at the top and bottom we have aluminum adherent, and in the middle we have adhesive. So now in the next step, I'm going to do a step. So again, initial is going to be a static. Click on continue and turn on a nonlinear, and for a number of the increment, increase this one to 10,000. Increment size, we can make this one, let's make this one 1 E minus 5, and make this one, the minimum is going to be 15. Again, if you want to know more about this, please check the video about step, where I'll explain all of this more in that video. Click on OK, and then I'm going to go to interaction. That I've already done it, so we don't have to do anything else here. Oh yeah, so there is one more thing that I want to do here, because what I'm going to do, I'm going to apply a displacement at the end. Okay, normally in Abaqus you cannot apply a load to a line. So if I try to apply a concentrated force, you'll see that I cannot apply to the line. I can only apply to a node. And if you remember in the load section, I explained that we can solve that by coupling a line to a node. However, if I want to apply displacement is possible to apply. So if I go here, displacement, I can apply displacement to a line. But the problem is that when you apply displacement to a line, and especially if you have a large displacement, will cause a mesh distortion around this area, and that might cause an issue. So I recommend you to again do the same thing and create a point here or node, and couple this one, that point to this line, so you won't have the mesh distortion problem in that area. So what I'm going to do, I'm going to go to interaction. From here I'm going to use a node offset from a datum point. So I'm going to select this one, and I'm going to say I want to offset it in the X direction. So I'm going to put 5, 0, and 0. So that 5 value that I put here is not going to really change the result. You can put 10, 20, you'll see that the result is not going to change. This is just to have a clear, a visible point basically. I don't want it to be too close to the line. So click on enter. So I have this point here, and I'm going to transfer it to a reference point. And what I'm going to do next step is to basically create a constraint, and I'm going to use coupling, and it will ask me to select the constraint control point, which is going to be this one. Click on OK, and I'm going to select the node region, this one, click on done, and keep the parameter as it is, and click on OK. So as you can see, now I couple this point to this line. So if I apply displacement to this point, it will apply to this line. Okay, so now I'm done with interaction. I'm going to go to load. So what we're going to have fixed in one side, and we're going to pull it 5 mm from other side. So I'm going to apply a full fixed at the back here, this line, I'll make it fixed, and I'm going to apply displacement to the other side, and so it's going to be 0 and 0 in a y direction, and the rotation is 0, and it's going to be 5 millimeter in an x positive direction. So click on OK. So that's going to be my basically displacement. Next step is mesh. So we can apply mesh in assembly, because in the assembly section we selected dependent, so it's going to be mesh on a part rather than mesh on an instance. So from here in the mesh section, I'll go to part, and I'm individually going to mesh these one. So what I want to do, first of all, I'm going to select mesh control and select these two, and because it's possible to apply structure mesh, I'll select the green one, so that will turn green, and then I will define a number of elements. So let's see what is the default value. So if I apply a default value, you see that I have a very large element. So I'll reduce this one to 0.5. Let's see how does it look like. Yeah, that's fine. And click on OK. But there is one point that you need to always consider when you mesh your part. If you look at the assembly here, we know that the significant part of stress is going to be in a bonding area. So we don't really need a high resolution mesh in these areas, because nothing's going to happen in this area. Everything's happening in at this point. So having basically a mesh with a mesh size with 0.5 in this corner, basically we are increasing our computation unnecessarily. So it's not really useful to have that. What I can do, I can change the mesh size here. So I'm going to select the top and bottom line, click on OK, and I'm going to use this single and apply this. And as you can see, I have a higher mesh concentration in this area. So what I'm going to do, I'm going to say the minimum value that I want is 0.5, and the maximum, which is going to be around this area, is 3. So if I apply this one, you'll see that the mesh, which is 0.5 here and 0.5 here, gradually will increase to 3 millimeter at the end here. So if I click on OK and apply a mesh, you see that I have a much finer mesh in a bonding area and coarser mesh in that area. And then what I also can do for the top one, so I'm gonna apply again the same structure mesh, and then I'm gonna select all of these, make it first 0.5, and then I'm gonna select the top and bottom and click on OK, and then go to single, make the minimum 0.5, and this one 3 millimeter. So again we have a 0.5 here and 3 millimeter in this side. So if for any reason your direction is not correct, you have to flip this one. So you basically only click on select and you click on done. It will just rotate that one. And if I apply it, you'll see that now I have it in this corner. But so basically flip it if yours is wrong. So again, as you can see, we have 0.5 and the mesh will gradually increase. Click on OK and assign a mesh. So we have this one as well perfectly. And now I'm going to do this one for adhesive. Same structure mesh. I'm going to apply 0.5. But what I want to do, I want to have a higher number of mesh in the thickness direction. So if I select this one and this one, click on OK, and let's say I'll make this one 25. Let's see how many elements we have. So we have 4 elements. So you see 1, 2, 3, 4, and click on OK and assign a mesh. Yes. Okay. So if I go to assembly, you'll see that how the mesh will change gradually from the fine mesh in this area to coarse mesh. We can also do it in a thickness direction as well. So as you can see, I have a smaller mesh in this area, and I can do the same thing for this one. It's not necessary, but we can do that. So if I go to a thickness direction, so I can select this one, and this one at the end, click on done, and if I say single and I make the minimum 25 and a maximum 0.5, it will ask me that it's going to remove the old mesh. I'm happy with that. So click on apply and assign a mesh, yes. So if I go back to assembly, you'll see that, oh yeah, I selected the wrong direction. So if I go to again this one, that was a bottom one, so it should have gone to the top. So if I select these lines again and flip this one and assign a mesh, and if I go back to assembly, you'll see that how the mesh will gradually decrease when it reaches the adhesive. So we'll have the same mesh size. And again, I'm going to do the same for the top one. So this is going to be this one, and this one. Click on done and single, make this one 0.25 and 0.5, and let's see if it's okay. Yeah, it is. Click on apply and assign a mesh, yes, and go back to assembly. We'll see that how the mesh will increase gradually in thickness direction. So there are 2 points here, very important one. The first thing that you don't want to do when you apply mesh is a big jump in terms of the element size. So you don't really want to have 0.5 and suddenly 3 millimeter. This is not really a good mesh. So you want your mesh size to increase gradually if you're doing that. So you cannot apply suddenly 0.5 here, and after this line you apply all of them 2 millimeter. That's not a good mesh size. The second point is that when you have a different part like this, you don't want your mesh in the second part end up here. So you want the node to contact each other at the exact position. So as you can see, I have one node here, one node there. Same for the top one, same for the bottom one. The bad mesh is when you have the, for instance, for top one from here to here, but for a bottom one you have it, for instance, from here to in the middle. So this is not something good, and you have to always make sure that you have the as much as you can, you have to make sure that the nodes, they're contacting each other at the same position. So we are done with the mesh, and I'm going to go to a job, and I think that we have done everything hopefully correctly. So if I create a job here, and I'm going to call this one SLG, which is a single lap joint, click on continue, okay, and I'm going to submit a job. Job submitted. I can monitor the job. So I didn't get any error in the step section. So if you get this one, that means that you have done everything correctly. And as you can see, the job is done. It's not really a heavy simulation. After 28 increments, so dismiss this one and show result, and select on plot, and you can see that the stress concentration is in the bonding or singularity point when the adhesive ends and we have the adherent. So this is the point that we have a highest stress concentration in terms of the wound misses. But if I go to normal direction, you'll see that the stress is in the adhesive. So this is a location that normally in a brittle adhesive the crack will initiate, and you would have you will barely have a cohesive failure. You normally have an adhesive failure, so which is going to be a failure in the interface between the adhesive and adherent. And also we can see the shear one. So next step for us is to plot a stress, and we can plot that using a path. So I can create a path anywhere in this geometry to basically plot a stress, and that's the most useful one in comparison to just like this one without a path. If you plot this one, is kind of like a painting, but if you want to export a meaningful result, is to basically use a create path and select this one. So I would say mid adhesive. I'm going to call this one mid adhesive, so that comes from the middle of adhesive. And so I'm going to select add before, and I'm going to select, so 1 2, so it's going to be this one, this one, this one, this one, this one. So I can see that the node, it will increase from 104, 103, 105, 106. So if I try to increase this one to, let's say, 150, see what happens. So as you can see, 150 comes up to here, and I can say add after, select this one, and the last one. Okay, so this is a one way of quickly selecting the nodes, because normally the node numbers has a logic behind it. So as you can see, how the node will change when you have 100, 300, 400, 500, 600, 7, especially in a simple geometry. But sometimes when you have a triangles, you might struggle, but most of the time there is a nice logic behind the node number. So that's a quick way to select all these nodes. Click on done. So I have this line in the middle, click on OK, and if I go to here, XY data, right click on this one, create, and if I select the path and click on continue, and I have this mid adhesive. So as you can see, in mid adhesive it selects the top and bottom element, so it selects all the things in the middle, and so currently the plot is at shear. So if I click on plot, you'll see that we have kind of like this is a stress in megapascal, because we are using a millimeter unit system, and as you can see we have a very high stress at the corners. So you have to make sure that the stress value can be positive and negative, and negative value doesn't mean that the stress is smaller, it's just in the other direction. So this is the highest stress is in this corner, and we have a lowest in the middle of the bone line, which is obvious. And as you can see, the distance is true distance, so it's 0 to 25. That was a basically length of the adhesive. What we can do, we can normalize the distance, and if I normalize, it's going to be 0 to 1. So basically what it would do, it would divide each location to 25, and you would have 0 to 1. And also you can do that yourself to stress, and you can normalize it, and they normally use a shear plot to normalize it. So they use the shear stress to normalize this curve. So I'm gonna do the same for, let's say, S22, which is a normal one. Let's see what happened to that. So if I select create part path, and I'm gonna do that for the, let's say, do it for true stress. So again, as you can see, we have very high stress point at the corners and low in the middle, and so I can do it for the normalized as well. So it's going to be 0 to 1, and also I can save this one, and I can say, for instance, S22 result, and so I have this one here, S22 result, and if I go to plugin tools, Excel utilities, I can select this one, click on OK, and I will have this one in Excel file. So this is a way of basically exporting your mesh result, sorry, exporting your stress result. So as you can see, it's normalized 0 to 1, and also you can do the same thing for the stress value. For instance, if you just divide it to the maximum value of the shear or normal stress. Also, we can export a result from the applied point. So we have a displacement and force from that point. So what I can do, I can go to create ODB field output, and from here I can select unique node, and what I want a reaction force, magnitude, and displacement, and I can select this element here that I cannot currently see, but I know that is in this location, so that's a way of finding it, like this, and click on done. So I see that I select the one node selected, click on plot, and so as you can see, I have reaction force in purple, and I have displacement in brown. So I can save this one. So I have two separate basically curve, and I can combine them using Abaqus. So I go to create, and I can use operate on XY data, click on continue, and then what I can do, I can select combine, and I can select displacement and then reaction force, and plot this one and save it as load displacement. So what I will have, I'll have a one curve, which the x comes from the displacement and y comes from force. And obviously this value is basically it's linear because we don't have any sort of failure criteria in our joint. And normally joint doesn't, this type of joint, especially with a brittle adhesive, it's not going to deform 5 millimeters. So 5 millimeters is too much. But if we had any sort of failure criteria, this joint would fail after less than a millimeter displacement, normally 0.7, 0.84 brittle adhesives. But because we don't have that failure criteria, we only have a linear one, which starts from 0 and linearly going to go up. So it doesn't really matter what displacement is going to you apply, this force is going to go up without any sort of failure until you put that failure criteria in your simulation. But again, as I mentioned, this is a basic Abaqus tutorial for you to learn the concept and to learn the software. And if you want to learn more about failure criteria, for instance, for adhesive, for composite, for metals, you can check my tutorials. Thank you so much for watching this tutorial, and I hope to see you in the next video. Thank you.